Okay, man, you covered a lot of topics. This is it's been a very wide range of topics. That's pretty awesome, actually. It's a quite a series of videos here. All right, so in this problem, there's how do I want to put this? Okay, so the first part of the problem is actually key to the problem, but from then on, you essentially has to use solubility product, um, equilibrium constants from then on. It's fairly benign use, but let me go ahead and point out the first part. A little caveat here, okay? So you would hit that link, you would go to the table of KSPs, you'd find your AGCL and AGCN. Notice I put in a search to find me AGC to save me time. Um, I find that AGCL has a 10 to the negative 10 solubility product. AGCN has a 10 to the negative 17. What does that mean? Well, it's a solubility product, meaning the solubility would be the top component, the soluble components would be on top, and of course the solid is a pure solid, so it doesn't actually go into the equation, but it would be the reactants, which are typically going to be on the bottom. So if it's a very small number, then that means it's going to be very insoluble. If it's a very large number, it means it's going to be much more soluble. Both of these are fairly insoluble. We would normally consider them insoluble. In fact, you may notice the silver chloride that you use to test, you actually use silver to test for the presence of chloride in one of your labs. So, kind of neat. Anyways, so yes, AgCN will precipitate first, but keep in mind there's a caveat here. Both of these are a 1-to-1 ratio between the cation and anion. If this had been one of these Ag2s right here or Ag3, you could not directly compare these KSP numbers to each other. You would actually need to go ahead and compare the equilibrium expressions to each other, if that makes a little bit more sense. If that doesn't make any sense, talk to me, okay? But because they are a 1-to-1 ratio, you can directly compare your KSPs, and there's no problem, okay? Uh, but yes, it would make a big difference if it was a 2 or 3 ratio, because it would take twice or 3 times the amount of silver ion to precipitate those out, right? So keep that in mind. The second part of the problem is that you need to figure out the concentration of silver at your first equivalence point. Well, what is your first equivalence point? Your first equivalence point is always where your moles of silver would match your moles of cyanide. But just because those moles match each other does not mean that all of it is precipitated. Or another way of thinking about it is, even if you precipitated all of the cyanide, it would automatically achieve equilibrium and some of that would dissolve. How much of that would dissolve would be its solubility. And how do you figure out solubility? Well, you can just directly plug in your numbers for your KSP. So your KSP in this case would be your silver concentration, and again is 1 silver to 1 cyanide, so you get powers of 1, which is nice and convenient. So your silver concentration times your cyanide concentration. You have your KSP value, it was that table. And so you plug your KSP value in. Whatever silver is released is going to be the same amount as whatever cyanide is released. Because remember, you put in exactly enough silver to match the amount of cyanide. So whatever amount of cyanide you have is going to be the amount of silver and vice versa. And so your KSP is just going to equal x squared. You go ahead and take the square root of both sides, and that's going to give you x, but x is also your silver concentration. So that'll give you your silver concentration. For these numbers specifically, it would be 7.73 times 10 to the negative ninth molarity. And the molarity's over there. Okay, so once you have your silver concentration, well, now you have a concentration of silver that's floating around in solution. And the next thing it's going to ask you is, well, would this cause that other species to start precipitating? So if there's a large enough difference between these KSPs, you could actually have one precipitate without any precipitation of the other. However, if there's not a particularly large enough difference, you'll get first, in our case, the silver cyanide precipitates. And then as the silver cyanide is still precipitating, you'll get some of that silver chloride precipitating. And what we're doing is we're trying to figure out, does that happen? Now, there's a fairly easy way to do that. And so what you do is you're going to go ahead and figure out what's called a reaction quotient. Really, you just do the same thing you would do for a KSP. You're just not sure if it's at equilibrium. So if it was at equilibrium, then everything that's going to precipitate is precipitated. If it's not at equilibrium, then you are going to end up with equilibrium will be the KSP, which would be where you get a precipitate, okay? So if you're above that number, then you're going to get a precipitation. So first thing you need to do is you need to go ahead and figure out your new concentrations, because you've diluted this quite a bit. So to determine if your AgCl is going to precipitate, because that's the one that hasn't precipitated yet, due to reaching the equivalence point for the AgCN, we're going to go ahead and calculate a reaction quotient. Your reaction quotient would be represented by Q. It's the same thing as a KSP, it's just not necessarily at equilibrium. It can be any other state. If it happens to be the concentrations that would give you equilibrium, then the Q, it was actually a KSP. Okay. So you need these concentrations of Ag plus and Cl minus to go ahead and figure out your Q here. First thing you should do is go ahead and figure out the Cl minus. So right here you have the 55 milliliters. Let me see if I can get up to where I have those numbers. The 55 milliliters. You have the KCN and KCl, and it's titrated with 0.106 molarity AgNO3. So you have your 55 milliliters of the KCN. It would be 1 mole of the AgNO3 would give you 1 mole of the KCN. Okay, kitty. All right. In this case, we're really kind of working this in millimoles, but that's okay. It's not gonna actually hurt anything because you'll see that milliliters will actually cancel here. Okay, and so then this right here would be the amount that takes of the AgNO3 to fully reach that equivalence point. Essentially what we've done is we've gotten millimoles of KCN. It's a 1-to-1 ratio between the silver, Ag, and the Cn to make AgCN. And then we've taken the moles here divided by the moles of AgNO3, and that gave us our milliliters of the AgNO3 that would take to do this titration. Once we have the milliliters it would take to do the titration, well, now we can go ahead and figure out what would be our new concentration for Cl-, because we've diluted this solution quite a bit. We've put 32 more milliliters in here to dilute it, 32.5. So we do an M1V1 equals M2V2 to get the new concentration of Cl-. That means we take the concentration we were given, we multiply it by the volume we were given, and then we divide it by our new volume, which is 55 plus the 32.5 milliliters. And that would be our initial concentration of our Cl-. So now we're seeing, are these values, are they going to be greater than or less than or equal to our KSP? So we take our silver concentration, which we actually just figured out. That's that right there. So we would have had to figure that out no matter what. We take that silver concentration, we multiply it by our chloride concentration, which we just figured out, and that would give us our value for Q, which is our reaction quotient. Now, if the reaction quotient is greater than the KSP, which if you remember your values for KSP, it's a lot larger. This is 10 to the negative 17. This one's 10 to the negative 10. So if our reaction quotient is greater than KSP, that means we're going to have too much dissolved, and some of it will precipitate. One of the ways you can think about this is that this number on the top here is too large, so it needs to become smaller. How would these numbers become smaller? Well, they would get used up to precipitate the salt. Hopefully that helps. Anyways, so our KSP is a smaller value than our Q in this case. That means the reaction is going to favor the precipitation, and that means that we will get some AgCl precipitating before we can finish precipitating all the AgCN. Let me know if you have any problems with that, if you don't understand anything. There's other ways we can talk about and describe it, but I need to know if this method doesn't work or not. Thank you, and let me know if these videos help, okay? Bye-bye.